Good evening, everyone. Welcome to week 3 problem solving session. Today I'll be discussing questions related to week 3 lecture. So let's start. So the question number 1 is the number of electrons present in the 5-star orbitals of NO plus in its molecular orbital diagram and the bond order respectively are. First option is 0 and 3. B is 3 and 2.5. C is 4 and 2 and D is 1 and 2. So here we are given NO plus which has two different atoms, nitrogen and oxygen, and in nitrogen there are 5 valence electrons, and for oxygen there will be 6, but since there is a positive charge, the total valence electrons will be 10. Since the oxygen is more electronegative atom, their more orbitals, atomic orbitals will lie lower in energy compared to nitrogen. So let's draw the energy diagram. So first for nitrogen there is 2p and 2s, and 2s2 and 2p3. And for oxygen it's 2s2 and 2p6 for atomic orbital of oxygen. Since oxygen is in its plus state, only 5 electrons will be there. So let's draw the molecular orbitals. So, sigma 2s, sigma star 2s, phi 2p, and sigma 2p, phi star 2p, and will be sigma star 2p. So sigma 2s and sigma star 2s, there will be 2 electrons each, and there are a total of 6 electrons here. So it will be filled in pi 2p and sigma 2p. So the bond order will be number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital divided by 2. So here there are 6 electrons in bonding molecular orbital. So 6 by 2. There is no electrons in anti-bonding, so it will be 6 by 2. So 3. So bond order is 3, and in pi star there is no electrons. So the answer is option A, 0 and 3. The next question is aluminum carbide, that is Al4C3, reacts with D2O to yield. Option A is aluminum and OD thrice plus CD3. B is aluminum OD twice and C2D2. And C is L OD thrice CD4. And D is aluminum OD thrice and C2D2. So we have seen the synthesis of hydride with the, 4 different synthesis methods, and they were direct combination with molecules. Like O2, so that like 2H2 plus O2 giving 2H2. Second was reduction. Oxide using strong reducing agents. Like lithium aluminum hydride. And third was uh, reduction of metal phosphine, carbide and silicide. Then fourth was in the conversion of hydride. So the chemical reactions with H2O and D2O with other molecules are similar. So we can match the reaction of water with that of D2O. So we are given aluminum carbide. So in this 4 cases, it's the third one, reduction of metal carbide, that is aluminum carbide. So we can write it in the form of water, that's Al4C3 plus H2O will give aluminum hydroxide plus CH4. So if we do the chemical balance, should be 4 aluminum is present. So there should be 4 aluminum hydroxide, then 3 carbon. So there should be 3 CH4. So the balance is we need to balance for water. So there are 12 OH and 12 hydrogen on the product side. So there will be that is if we add it, it will be 12 H2O. So we'll need 12 H2O to convert aluminum carbide into aluminum hydroxide and methane. So we'll take this mechanism and we can do the reaction mechanism with D2O. So it will be Al4C3 plus 12 D2O will give 4AlOH thrice plus 3 OD thrice plus CD4. So this will be the reaction mechanism. So the question was aluminum carbide react with D2O to yield aluminum OD thrice and CD4. So the answer is option C, The next question is the correct order of the melting points of hydrates of group 17 elements. Uh, so option A is hydrogen iodide greater than hydrogen bromide greater than HCl greater than HF, and B is HI greater than HF greater than HBr greater than HCl. C is HBr greater than HI greater than HCl greater than HF, and D is HF greater than HBr greater than HCl greater than HI. So the periodic trend for melting points and boiling points of hydrates is they increase while moving down the group because the increase in size of the molecules and increased interactions. That is when we in the periodic table when we move down the group, uh, melting point and boiling point increase. But in the group 15, 16 and 17 among the hydrates there is some anomaly, and uh, this trend was already discussed in the lecture. So we can see here that for uh, group 14 for the carbon family, the trend is what we expected. That is when we move down the group, the melting point is increasing for hydrates. So first CH4, then silicon hydride, germanium hydride, and tin hydride. So the trend is melting point increasing with increasing atomic number or while moving down the group. But in the case of group 15, group 16 and group 17, so the trend is a bit different. The first hydride of first elements, that is uh, for nitrogen ammonia, B the second one for the oxygen group water, and for the halogens HF. So all these three shows very high melting point compared to their next hydride of next elements. So this difference in trend is because of the presence of hydrogen bonding in water, ammonia, and HF. So they show a very strong hydrogen bonding. So the melting point and the boiling point increases compared to the hydrates of elements in the same group. So the trend for H halogens is that hydrogen fluoride is greater than HCl, and it's also greater than HBr, but HI is the highest. So the option B is the answer. HI greater than HF greater than HBr greater than HCl. And question 4 is silane, that is SiH4 reacts with O2 to give. So option A is silicon oxide plus H2O, B is silicon dioxide plus H2, C is silicon dioxide plus H2O, D is silicon oxide plus H2. So in the lecture we have learned that P block hydrates are reducing agents. So when we expose these hydrates to O2, or they can undergo combustion, which will produce their oxide and water. So for example, if we use methane CH4 and 2O2, it will give corresponding oxide CO2 plus water. So similarly we can do for silane. SiH4 plus 2O2 will give silicon dioxide plus 2H2. So the answer is option C, silicon dioxide and water. So the next question is the total number of orbitals contributed by fluorine atoms in the molecular orbital diagram of BF3 molecules. So for BF3, first we'll draw the MO diagram. So boron has 3 electrons. In 2s there are 2 electrons, and in 2p there is only 1. So in fluorine there are 3 fluorine atoms, and so in each fluorine there are 2s and 2p orbitals. In 2s there are 2 electrons, and in 2p there are 5 electrons. So there is 1s and 3p orbitals. So in 3f means 3 into 4, that is 12 atomic orbitals will be present. So it will be acting as 12 ligand group orbitals. So there will be 12. So they'll combine with each 2s and 2p. So first they'll form bonding molecular orbital. So A1 dash, then 2 degenerate orbitals, then A2 dash. This one is A1 dash, and this one is A2 double prime and E prime, and A2 double prime is PZ, and E prime is PX and PY. And antibonding orbital will be A2 double prime star and E prime star, then A1 star. So A1 prime is formed from 2s and the ligand group orbitals, and it forms an antibonding. And next one is E prime. It's formed from 2p and LGO, and it forms an antibonding. And A2 double prime is also formed from 2p and LGO. So the for bonding and non-bonding by combining with atomic orbitals of boron and ligand group orbitals, and 8 of them will remain as non-bonding. So first the 6 electrons from boron and the 3 electrons from boron and 3 electrons, that is 2s2 and 2p. So there is one unpaired electrons in fluorine. So there are 3 fluorine atoms. So each of them contributes 1 electron each. So there will be 3 electrons from fluorine and 3 electrons from boron. So total of 6 electrons will be filled here. And there will be this is the Lewis structure for BF3, and each fluorine will be having 3 lone pair of electrons around it, and here boron has only 6 bond pair of electrons. So one of the fluorine will be donating electron to uh, boron, so that octet of boron is completed. So there is a back donation of electrons. So there will be 8 electrons in the bonding orbitals. So now the Lewis acidity of boron is reduced because of this uh, back donation, and there are in boron there is 3 electrons, and in one fluorine there is 7 valence electrons, and we have 3 fluorine, that is 3 into 7, that is 21 electrons. So total of 21 plus 3, that is 24 electrons. So there is we have given 8 electrons in the bonding orbitals. So 24 minus 8 is 16. So 16 electrons are remaining. They will be occupied in the non-bonding orbitals. So the total number of orbitals contributed by fluorine atoms in M of BF3 is 12. The next question is sodium amalgam reacts with water to give. Option A is sodium hydride and uh, mercury hydroxide. B is sodium hydroxide, hydrogen gas, and mercury. C is sodium oxide uh, and hydrogen gas and mercury. D is HGS and sodium hydroxide. So the given reaction is one of the method to produce hydrogen gas, which is electrolysis of brine using mercury as electrode. So the reaction was if we use 3 to 26% of sodium chloride solution, and mercury as the electrode, we'll get sodium amalgam and chloride gas. So there is 2 Cl here, so we'll have to balance it. 2 NaCl and Cl2, and 2 Hg will be 2 NH. Yeah, so this one is balanced. So after this, we'll use this sodium amalgam, which is the given question. 2 NaHg liquid plus 2 H2 will give sodium amalgam with water will give sodium hydroxide plus hydrogen gas plus mercury. So the reaction will proceed like this. Sodium amalgam plus water will be giving sodium hydroxide, then hydrogen gas and mercury. So the option B is the answer. And, next question is the syngas reaction is option A is carbon plus water giving methane and oxygen. B is carbon monoxide plus water giving CO2 plus uh, hydrogen gas. C is CO2 plus H2 giving carbon monoxide and water. D is carbon plus water giving carbon monoxide and H2. So syngas is the CO2, CO and H2 gas mixture in 1:1 ratio. And they are called as syngas because this mixture can be used to synthesize uh, higher alkanes and other hydrocarbons. And so here we'll have to find where CO and H2 is produced. So so here C plus H2 giving CO plus H2, which is the syngas. So option D is the answer. And next question is among the following, the diamagnetic species are option A is C2 and O2, B is O22 minus Li2 and N2 plus, C is C2, O22 minus and Li2, D is Li2 and N2 plus. So we have uh, five different molecules: C2, O2, O22 minus, Li2 and N2 plus. So we'll look at molecular orbital diagram for each. So first one is C2. So one carbon has 4 valence electrons. So in C2 there is 8 valence electrons. And the molecular orbital diagram will be 2s2 and 2p2. So we'll add the electrons in molecular orbitals. There are a total of 4 electrons in 2p, so it will be added in 5. So all the 4 will go into 5. So the bond order is uh, 4 by 2, 2, and all the electrons are paired in C2. And next one is O2. So in O2 there are 12 valence electrons. So in oxygen 2p there are 8 uh, valence electrons. So we have to add it in sigma 2p, then 4 of them in pi 2p, and 1 each in pi star. So there is 8 valence electrons in sigma 2p, pi 2p, and pi star 2p. And there are 2 unpaired electrons here. Here all are paired. And next one is La2. So in Li2 only 2 valence electrons are there. So, so uh, 2 of the electrons are occupying in sigma 2s molecular orbital. So there is no unpaired electron. And next one was N2 plus. So in N2 plus there are 9 valence electrons. So there are 6 electrons in 2p. So it will be filled in pi 2p and sigma 2p. So there are no unpaired electrons here. For it was N2 plus, so one electron will be less. So it will not be paired. So if it was N2, then there will be 6 electrons. But since it's N2 plus, there will be 1 electron less. So one will be unpaired in sigma 2p. So one unpaired will be present. And the next molecule was O2 2 minus. So in O2 2 minus, there will be 14 valence electrons. So there will be 7 valence electrons in 2SN2p. So there are total of 10 electrons in 2p orbitals. So we'll fill it in sigma star to sigma to sigma 2p pi 2p pi star 2p and so we'll fill it in sigma 2p pi 2p and pi star 2. So there are total of 10 electrons in sigma 2p pi 2p and pi star 2p. So all of them are paired, so it will be 0 unpaired. So there are in C2 0 unpaired. In O2 there are 2 unpaired electrons, and in N2 there is 1 unpaired electron. In O2 2 minus there is no unpaired electrons, and in Li2 there are no unpaired electrons. So we'll write it here C2 no unpaired electron. In O2 2 unpaired electrons. In O2 2 minus, no unpaired electrons. Li2, no unpaired electrons. And then N2 plus 1 unpaired electron. So the question was which are the diamagnetic species. So diamagnetic species is the species having no unpaired electrons such that the total magnetic moment will be 0. So here C2, O2 2 minus and Li2 will be the diamagnetic species. So the option C is the answer. The next question is correct order of bond energies. A is N2, N2 greater than N2 plus similar to N2 minus greater than N2 2 minus. B is N2 2 minus greater than N2 minus greater than N2 plus greater than N2, and C is N2 greater than N2 2 minus similar to N2 plus N2 minus. Option C is N2 greater than N2 2 minus similar to N2 plus greater than N2 minus, and D is the N2 minus greater than N2 less than N2 plus greater than N2 minus. So we need to see the molecular orbital diagram and the bond order for all these species N2, N2 plus, N2 minus and N2 2 minus. So first we'll go for N2. So N2 has 10 valence electrons. So there are total 4 electrons in 2s. So it will be in sigma 2s and sigma star 2s. And 6 electrons in 2p orbitals. So it will be filled in pi 2p and sigma 2p. So the bond order is, we can neglect this because it will get cancelled. And here there are 6 electrons in bonding a molecular orbital. 6 minus there is no electrons in antibonding, so it is 0. Wait, that is 3. So next one is N2 plus. So in N2 plus there will be 9 electrons. So we can draw the same molecular orbital structure. So in N2 plus, one of the electron from N2 will be missing. So one of the 2p is vacant. So there are 5 electrons that will be filled in by 2p and sigma 2p. So there are total of 5 electrons here. So the bond order is 5 minus 0 by 2. That is 2.5. And next one is N2 minus. In N2 minus, there will be 11 electrons. So 11 electron will be added like one will be 2s2 2p3 and other will be 2s2 2p4. So total of 5 plus 6 electron, that is 11 valence electrons. So the 7 electrons will be added in pi 2p is 4, then 2 in sigma 2p, and then it's 6, and there is one more electron present that will be in pi star 2p. So bond order will be 6 electrons in bonding orbitals and minus 1 electrons in antibonding. So 6 minus 1 by 2, that is 5 by 2, 2.5. And in next one it's N2 2 minus. So it will have same molecular orbital to N2 minus and 1 electron extra. So it will be 12 electrons. So the order of molecular orbitals will be similar. It will be sigma 2s2, sigma star 2s2, pi 2p, pi 2p1. They will be having 2 electrons each, 1 to 2 minus, and there will be sigma 2p, 2 electrons, and in pi star, so 1 electrons each. So there will be 12 electrons. We can count it 2, 4, 6, 8, 10, 11, and 12. So total of 12 electrons and 2 minus, which is arranged in this order. So bond order will be, we can neglect for sigma 2s and sigma star 2s. So in bonding, there will be 4 electrons in pi bonding and 2 electrons in sigma bonding. So total of 6 bonding electrons and 2 electrons in antibonding. It is 4 by 2 is 2. So we know that bond order is directly proportional to bond energy. or bond strength. So the order of bond order will be N2 is higher, then N2 plus and N2 minus are similar, and N2 2 minus. So the order is N2, then N2 plus or N2 minus, then N2 2 minus. So bond order is directly proportional to bond energy. So the same order will be following for bond energy. So the answer is option A, N2 greater than N2 plus equal to N2 minus greater than N2 2 minus. The next question is the reaction of lithium nitride, that is Li3N, with D2O gives. Option A is 2 lithium plus Nd thrice plus uh, LiOD. B is 3 LiOD plus Nd3. C is Li2O plus Nd3. And D is 2 LiOD plus Nd3 plus Li. So we have already learned that if we use a metal nitride and do reduction with water, we will be getting corresponding hydroxide and hydride. So if we use water with lithium nitride, that will be Li3N plus H2O will be giving lithium hydride, hydroxide plus hydride of nitrogen, that is ammonia. So if we balance the equation, there are 3 lithium. So this will be 3 lithium hydroxide, and NH3 is only 1, and we'll have to balance for water. So 3 OH and 3 hydrogen. So similar to 3 water. So it will be 3. So we can use the similar equation for reaction of lithium nitride with D2O. So Li3N plus 3 D2O will be giving 3 LiOD, right? Uh, LiOD plus ND. So option B is the answer. The next question is the number of electrons present in pi star orbital and the bond order of O2 respectively are. Option A is 2 and 2.5, B is 2 and 3 and 2, C is 2 and 2, and D is 2 and 3. So in O2 there are 12 valence electrons. So we can draw the molecular orbital diagram. That is 2s2 and 2p4. So 4 electrons in two 2s orbitals. So they'll be filled in sigma 2s and sigma star 2s. And in 2p there are 8 electrons that will be filled in sigma 2p, pi 2p, and 1 electron each in pi star 2p orbitals. So the question is number of electrons in pi star orbitals. So there are 2 electrons in pi star. And bond order will be number of electrons in bonding orbital minus number of electrons in antibonding by 2. So in bonding we can neglect these two because they'll cancel each other. Next one is there are 6 electrons in bonding and 2 electrons in antibonding. So 4 by 2, that is 2. So bond order is 2 and number of electrons in pi star is 2. So option C is the answer. So the next question is water gas shift reaction is given by A, CO2 plus H2O giving CO3 plus H2, B is C plus H2O giving CO plus H2, and C is CO plus H2O giving CO2 plus H2, and D is CO2 plus H2 giving CO plus H2. So the water gas shift reaction is the conversion of CO using water into CO2 and hydrogen gas. So hydrogen gas will be generated along with CO2. So the option is option C, CO plus water giving CO2 plus H2. So this is a water gas reaction. And you should know that the syngas is CO plus H2 in 1:1 ratio. So they are both different. In syngas it's CO and H2, and in water gas shift reaction is CO is reacted with water so that H2 is generated. So the next question is Ca3P2 plus 6H2O giving A plus 3 calcium hydroxide, where A is, we have to find what is A. Option A is 3H2PO3, B is P2O5, C is 2PH3, and D is H3PO4. So this is the simple balance equation, but we have already seen some of the reactions to produce hydrates. So we are given metal phosphine, that is Ca3P2, and it's hydrolyzed. So we know that from hydrolysis of metal phosphine we get hydrates and metal hydroxide. So Ca3P2 plus 6H2 will be so we are expecting to get hydrate. So hydrate of phosphorus, that will be pH, and we'll have to balance the equation. There are 3 calcium, it's balanced in right side, 2 phosphorus, so it will be 2. For hydrogen and oxygen, this is 6 OH plus 6H, it will be 6H2. So all balanced, so it will be 2 pH3. So option C is the answer. Next one is calcium carbide reacts with D2O2 form. Option A is CaO plus C2D4. B is 3C2D2 plus 3CaOD twice. C is C6D6 plus 3CaOD twice. And D is CaO plus C2D6. So D2O is a weak reducing agent. So if we had used strong reducing agent like lithium aluminum hydride, we might get CH4. But since this one is a weak reducing agent, only partial reduction will be obtained. So CaC2 plus 2D2O, it will be CaOD twice plus C2D2. That be so option B is the answer. Where this one calcium OD twice and C2D2. And next question is silicon tetrachloride reacts with lithium aluminum hydride in 1:1 ratio will give A is SiH2Cl2 plus LiAlCl4, B is SiH4 plus LiH plus AlCl3, and C is SiHCl3 plus LiH plus AlCl3, and D is SiH4 plus LiAlCl4. And here we are given a strong reducing agent. So reduction of halides, that is SiCl4. So SiCl4 plus a strong reducing agent, that is LiAlH4, that will give hydride of silicon. So that will be SiH4 plus LiAlCl4. So the answer is option D. The next question is classify the following into ionic, covalent and metallic hydrides. There are given that H2S, NH3, BH3, ALH3, CH4, sodium hydride, calcium hydride, lithium hydride, beryllium hydride, and ReH9 2 minus. So there are three different classifications. That is ionic hydride, which are mainly formed from alkali and alkaline metals. And the second one is covalent hydrates, which are formed from p block elements. And next one is metallic hydride, that are formed from transition metal or d block elements. So here it's the periodic table, and from here we can characterize, classify each of these hydride. First one is H2S, and the sulfur is in the P block. So it's a covalent. Covalent H2S. So H2S in covalent hydrates. Next one is NH3. So nitrogen is also in P. So NH3 is in covalent. And next one is PH3. So phosphorus is also in P block. So PH3 is covalent. And next one is ALH3. So aluminum is also in P. So it's a covalent. Then CH4, carbon is in the P block. So CH4 is also a covalent hydrate. Next one is sodium hydride. So sodium is in the alkali metals, so it's a ionic hydride. Um, and it's in ionic. Then next one is calcium hydride. So calcium is in the alkaline earth metal, so it's a ionic hydride. Next one is lithium hydride. So it's in the alkali metals. So lithium hydride is an ionic hydride. Next one is the beryllium hydride. So it's also in the alkaline earth metal. So it's an ionic. Next one is metallic hydride. Rhenium hydride is given. So rhenium, it's present in the D block. So it's a metallic hydride. Next question is classify the compounds PH3, cesium hydride, and B2H6 into electron deficient, electron precise, and electron rich. So electron deficient is defined as molecules having electrons less than octet in the Lewis structure. So molecules with less electrons than octet. Next one is electron precise. Molecule satisfying octet, and there will be no lone pairs. And next one is electron precise. That is molecules with octet and will be having lone pair of electrons. So here first one is pH3. So phosphorus is having 5 valence electrons and hence bond with hydrogen. So its octet is complete and one lone pair is present. So this one is electron rich. Next one is cesium hydride. So cesium has only uh, one electron in its valence. It forms a bond with hydrogen, so it's satisfied. So it's a electron precise system. And next one is B2H6. So here uh, in B2H6, it's a boron has 3 valence electrons and yeah, so we can consider it like this. So if we split like this, one boron having only 3 bonds. So one boron has only 6 electrons in its valence. 6 bond pairs, 6 bond pairs surrounding one boron. So it's less than octet, so it is electron deficient. And next question is how does H plus exist in water? Option A is H2O plus, B is H plus, C is H9O4 plus, and D is H5O2 plus. So H plus doesn't have independent axis. So H plus will form bond with one water molecule and it will get hydrated by 3 other H2O molecules. So the structure will be uh, the H plus will be like this. It will form a bond with one of the lone pair. So it will like form H3O plus first, and all this will be polarized. So delta plus and delta plus. So each of these delta plus will be stabilized with 3 other water molecules. So this is how H plus will be existing in water. First, it will be stabilized as H2O plus, then hydrated with 3 other water molecules. These are the 3 water molecules hydrating this H3O plus. So it will be there are 9 hydrogen and 4 oxygen and the positive charge. So the option C is the answer. Next question is ionic hydrates and covalent hydrates react with water to give. So let's define ionic hydrate. Ionic hydrate. So ionic hydrates are formed from alkali and alkaline earth metals. And next one is covalent hydrate. And it is formed from p block elements. So in ionic hydrides, all the metal centers will be highly electropositive. So when they react with the water, it will form a basic solution of hydroxide and H2O gas will be released. So this will give hydroxide and H2O gas. For example, if we have sodium hydride and reacted with the water, it will give sodium hydroxide and H2 gas. So we know that sodium hydroxide is a strong base. So the solution will be basic. And in covalent hydrides, uh, they are formed from p block elements, and the hydride will be mostly polar covalent. And so when they are uh, added in water, they will get dissolved in water. So the solution will be mostly neutral or slightly acidic. So this is the end of today's uh, session. So if you have any doubts, you can ask.